Hello, everybody. So, as promised, the pre-recorded session. I will do the lab today in a pre-recorded way. We will see again on Wednesday. I'm sharing my screen now. We can briefly go through the syllabus. I hope you all have recovered now from the midterms and you're content with your grades. So we are essentially now on lab day, module 13. Practice lab 2 has been issued, has been assigned. It's due on 11/14, so next week on Tuesday midnight. And please submit as usual. It will only be an Excel sheet that we essentially will discuss now. I want you to calculate it in the same fashion as I'm calculating it, just to make sure we're on the same page and we are essentially doing the same exercise. You are expected to come to the same results, which you will if you do it exactly in the same way as I am doing it. So you have on Canvas, you have the examples. So the examples are essentially listed also here. Ignore the R part. So example number 1, we will not do R. This is because that particular lab is not necessarily benefiting from R to the fullest. So as thought, it would be worthwhile consideration to leave R out for this context. So there will not be any R coding necessary for today's lab, today's practice session. So you will only have to do you will only have to do it in Excel. Okay, so first of all, what you do in Excel, you are opening a new sheet. You are essentially having a sigma, and this is just, it is essentially the same as we have done now over the last exercises, and it's literally, it's just a repetition of what we've always done. Okay, so we have a sigma of, so we have the following example. So we have, you're conducting a SAT test on a sample of 50 people for whom you observe the mean verbal score on the SATs, university admission tests used in the US and other countries, of 542. So your sample mean, X bar, is 542. The population mean is 500, and the standard deviation is 100. So your sigma here is the standard deviation, right? So you essentially, you have a sigma of 100. You have an N of 50. You have an X bar, which we discussed. And you have a population mean of, this is the mu, of 500. And you have an X bar of 542. So how are you going to calculate that? So the spread of the population, the sigma m, this is easy to calculate, right? So the only one thing you have to do here is to essentially calculate your standard error of the mean. Okay, so mu 500, sigma 100, n 50, and the X bar is 542. So what's the first thing we need to do? We need to calculate the standard error of the mean, right? Standard error of the mean, SEM, equals sigma divided by the SQRT of the n, right? We know this. This is 14.142. So now we have 50 people in a random sample. We want to compare this. So step 2. So this is our step 1. So we're identifying our population, understanding what we're looking at. Step 2 is now our null hypothesis. So step 2 is the null is x bar equals mu. Right? And analogously, the alternative hypothesis is that x bar is not equal to mu. So I'm indicating this here with an exclamation mark because that's like a computer coding way of showing it. It indicates that it's different. So it's not smaller and it's not larger. Either or. So this is step 2 in our two-sided test. So now step 3 is to determine an alpha level. So what is our alpha level? It's 5%, right? So step 3A essentially is now to calculate the set score, right? So let's do first. Let's go step by step. Okay. So we go through all the 6 steps and we calculate the set score. So now let's do this a little different. So we do a separate table down here. We do null hypothesis, null alternative. We do set p is a proportion, and this is a percentage. So what does that mean? So we're doing two-tailed, and here we also need two-tailed one-sided. So we do one left-tailed, and we do one right-tailed hypothesis, right? So why am I doing this now? Because since we are essentially doing this and this, so okay, let's say the ones up later. So we want to, A is the spread of the comparing distribution. So this is here A, this is 2A. Then we have B, this is the 6 steps of hypothesis testing up until calculation of the set score. So this is B continued. So the set score is now X bar minus the mu divided by the standard error of the mean, right? We know this is the distribution of our P, of our set. So how do we get now the essential P value? So there's now a way to essentially do that, which is it's called norm dist as a function. You basically get you give it a set score, which is here 2.9. You gave it a mean, which is here our X bar. You give it a standard deviation, which is now here our standard error of the mean. And you say it's a cumulative distribution function. And by that, you essentially you get here 0. Oh, just a second. Okay, so you have the set score. The P you get essentially, and read up to do for the formula. So we're going, so we have here an X, our X is the X bar. Our mean is the mu. And the sigma here is the standard error of the mean. And now we need to do true for getting a cumulative distribution function. We get 0.99. So 0.99 is now the P. So what do we have to keep in mind for that? It's not the P. This is the actual point. So we need to calculate the 1 minus P because we only want that end of the tail, right? And this end of the tail is 1 minus P multiplied by 2. And this is now 0.003. And so I'm moving this now down here because I want to indicate that it's 0.0015 multiplied by 2. And you can look this up on the set score table as well. We're going to do this now. When you go for 0.2.9, 2.97 minus 2.97, you have here 0.0015. And this is the same as this number multiplied by 2, right? And this multiplied by 100 to get to percentage gives us 0.3%. Probability is distinguished. So now we want to do the same thing for okay, so we did now the set scores, we did the hypothesis testing. Now we want to set score for a one-sided test. This is essentially now X bar. So this was a two-sided test, right? So this is our C. So if we do a one-sided test now, this is X bar. If we're saying it's left-tailed, that would be an X bar that is smaller than mu, right? With no wrong, that would be the alternative hypothesis. So X bar greater equal than mu, that would be the null hypothesis. So our set is still the same, right? Oops. So we need to lock in the values again if we move it. So now we have Now we have to approach this differently because now we're calculating as if it was smaller. So this means the research hypothesis is taking everything below, which means now we're not doing the 1 minus the p, because now we're only taking this assumption. So we are now looking at the research hypothesis. The research hypothesis says essentially, or the alternative hypothesis says that right now, so before we took two-tailed, right now we're looking at only at everything that is to the left of our set score, right? So we have a set score of 2.97, and this will not change. This will be like that arithmetically. So we have 2.97 and we're taking everything to the left. That means in this table, we're only looking at 2.97. And 2.97 here is 0.9985, which is the same value as this one, just without the 1 minus. And it's a one-tiled test, which we don't multiply by 2. No. And I didn't lock the thing. So now it's as a percentage, it's essentially this multiplied by 100. And this is important to keep in mind because now it's 0.99 multiplied by 1. It's because it's only a one-tailed test, right? So if we have now x bar is smaller equal than mu, and we do x bar greater than mu as the research hypothesis, now it's getting more interesting because now we're back to 1 minus. So now we still have the same set score, but now we only have the 0.0015 multiplied by 1 at this point. Right? So the only thing we need to do here, and if you look at the p-value, you see that you are essentially here rejecting the null hypothesis. Here you're accepting the null hypothesis because the p-value is greater than 5%. And for the one right-tailed, you are again rejecting it because it's smaller than 5%. So you're essentially now doing norm.dist with an x of 542, a mean of 500, a standard deviation of 14.14, and you're doing it cumulative. This is your 0.9985. However, since your alternative hypothesis is only taking everything greater than that, you need to do 1 minus this, okay? And this multiplied by 100, that's 0.15. Good. So this is how you do hypothesis testing in Excel, which you know already, right? So now we calculate now we're calculating the confidence intervals. You're easily doing that by, you do confidence intervals, you do upper limit, you do lower limit. You're calculating your x bar plus 1.96 multiplied by your standard error of the mean. That's your upper limit. And your lower limit is x bar minus 1.96 multiplied by the standard error. That's 514 and 560 or 579. So now is this containing your mu? It's not. This is where it's significantly different for two-sided hypothesis test. So this is example 7.29. Oh wait, we also need to do effect size, right? So effect size is easily, this is D. now we're doing my effect size. We're calculating the difference of x bar minus mu difference between x bar and minus mu divided by the standard deviation, the sigma, which is here an effect size of 0.42, which is consistent with a medium size effect size, I believe, right? Oh no, it's actually a small effect size. So, and this is 7.29. So now 7.3 is equally simple. We have now okay, easily solved. We have a population mean of 500. We have a sigma of 100 again. With an n of 132 and an x bar of 5490. So again, same story, right? Standard error of the mean equals sigma divided by square root of the n, which is 8.7. We have step 1, we're defining our populations. 132 US students going through all 6 steps. So we're essentially in step 2, we're defining the null, which is the same as before. It's x bar equals mu. Alternative hypothesis is x bar is unequal to mu. Research our alternative hypothesis. Step 3, we're defining an alpha of 5%. Step 3a, we can do again a little bit of a tabularic kind of format. Research hypothesis, set p proportion, p percentage, same thing, just multiplied by 100. The two-tailed one, left-tailed one, right-tailed, right? So our null is exactly this. Our set is x bar for 90. Our set is x bar minus the mu in parentheses with dollar signs, otherwise you can't transfer it, divided by our standard error of the mean. Oops. What happened here? Not $2 cents. That's not good. $B, $1. Okay, minus 115. Our P is now norm.dist norm.dist notably 1 minus norm.dist, because we want the tail, right? 1 minus norm.dist. Our x is 490. The mean is 500. The standard deviation is SEN, and it's cumulative. That's 0.87. So what does that essentially mean? So now we have, okay, that's actually, we need to actually not multiply by -1, but we need to multiply by 2. So we have now, what we have now is we have a negative value, meaning we need everything to the left of this. So if we're taking 1 minus this, we would get everything to the right, right? Don't forget. So we need to take everything to the left because it's a negative value. So this gives us a difference of 0.25, which essentially is now multiplied by 2 already. So now this is a proportion, is this, as a percentage is this multiplied by 100, so it's 25% probability that this is only due to random chances difference. If we're having an x bar, now we're doing the left side, right? X bar is greater equal mu. So x bar as a research hypothesis is now smaller than mu, right? So now we need everything to the left. What we're gonna do? Again, the set score is the same. Oh, so let's put on the directions. Got this one. Okay. So now we're not multiplying by 2. Do you remember how we did multiply by 2? We're not multiplying by 2 now. We're doing norm dist. Again, negative value, everything to the left, right? Norm dist 490, our x bar, our x, mu 500. Standard deviation is the standard error because that's the distribution of the sample means, and it's a cumulative distribution. Okay, so it's 0.12 now, right? So this is this, and this is this multiplied by 100. So now we're looking at the inward. So now we're doing a one right to the one-sided, one-tailed test to the right. So this means x bar is smaller equal mu in the null hypothesis, and x bar is greater than mu. So now we're again having the same set because the set doesn't change, the difference doesn't change, the standard error doesn't change either. But now we're doing the 1 minus norm dist, norm dot dist, and the reason is clear, right? Because now we're testing everything to the right of our x. So we're looking for everything greater. So we're looking for 1 minus our p-value. So 1 minus dist is now 490. Mean is still 500. Standard error is 8.8, and it's still cumulative. Now it's 87%. which is this multiplied by 100. Okay, and that's the second example. And this is pretty much all I wanted to do today. I will upload the R code. I did have an R code that essentially covers today's session. Save it. I will post it as an announcement. Save it, run it through if you want to see what it means. It's basically the same kind of calculation, right? So we have an RM with 7.29, we have the mu, we have the X bar, we get the N, we calculate the SCM, which is 14.14, 2.9 as the set, with the P2 tailed is P norm. So if you have a negative, so you want to take always the negative here because always the negative is the small one. So if you have a set and you're making, so if set equals -10 and you do abs set, this will always get you a negative. And if you always want to have a negative, you just need to do minus abs set because that's how it always will be negative. So it first sets it positive. So absolute value of something is always a positive value. And if you first set it positive and then you make it negative. So this is how you will always get this. Oops. I'll this one. Okay, that's how you will basically get your two-tailed test. If you do P2-tailed smaller, essentially you are getting now your 9985. So this is now rejecting the null. If you do P1-tailed greater, you essentially get here the P equals 0.0015, as we've done already. These are the confidence intervals, which we have calculated as well. So this is how you calculate them in R. This is how you calculate the effect size. Here the same example. You know what, now that we're actually talking about it, please do essentially also run the practice lab in R. So please just run this through, copy it in a text document, put your entire console into a text document and submit the whole thing. So first you need to run it, please run it, copy then everything. Okay, so you do this, you press Control and L, you delete everything that's there. You press Control and A and you run the whole thing too, okay? And then you just copy paste this in a text document, whatever's down there in the console. And then you upload both. You upload the text file, not the R code. Don't upload the R code. You will lose points if you do that. I need to take those points from you. Again, not for this one because I don't know. But yeah, please upload the text file and upload that Excel spreadsheet that you have followed now along. Okay. I will upload the R code. I'm doing this right now. But I should not forget it. I will upload the R code and I will wait for your submissions. So you have time until next week. So that gives you ample time to run the code and study the code. All right, so this was the pre-recorded practice lab 2. I think it's nice to kind of go through hypothesis testing with various softwares, see that they add up, that they yield the same results. And you can choose either or to then do your analysis in real life. Okay, good. We see you again on Wednesday. Have a good 2 days. And on Wednesday, we will be continuing with the single example t-test, where we essentially will firstly estimate the standard deviation from a sample rather than needing to know it from the population. So this is the next phase of hypothesis testing. All right, this is also where the lab is good, that you're kind of in the mindset and you essentially have repeated the SAT testing, and this is really solid in your memory. Okay, have a nice evening at this point, and I will see you on Wednesday in person class. Please don't forget. Yeah, I will test the attendance. Okay, bye-bye.